Thank you all for joining us in the Causal Effects Reading Group. First of all, some information about how we will organize this thing and some other technical information. The first thing to notice, and that I have to say here, is that we are recording the sessions. So if if you all agree, just don't say nothing, and if is there anybody that disagrees, just let us know. And I guess that everybody's happy with that, and yeah. And after the sessions, the idea is to publish this in the YouTube channel of ICMAT, just in case anybody could not join. Then some information about what is our idea about this reading group. The idea is to meet once per week. The established time is this time on Fridays at 12:15. We're going to do it both online and in person. In person is going to be in Orange Room at ICMAT. If there is any change at some point for a particular week, we will let you know. The idea is to start from the very basics of causal inference. And for that, we have chosen the What If book by Miguel Hernan, who is at Harvard, and it starts from the very beginning, so everybody could follow. And then the idea is to go into more complex details and maybe read 2 or 3 papers that we have in mind. And also we have a database that is related with cardiovascular diseases that maybe we can play with to apply the things we learn here. That's the basic idea. Then we want to have volunteers. Volunteers are welcome to join in order to read. This is a reading group. It's not a class. It's not a course. So the idea is that we all participate. For the first 3 sessions that are going to be today, Friday 16th and Friday 23rd, we have already volunteers. David and myself, we will cover the first 3 chapters of the book. And for the future, if anybody wants to volunteer, just let me know and we will assign some homeworks. It's very easy. You just need to read a chapter of this book or a paper eventually and explain it like I'm going to do today here, very briefly without, not a lot of detail, but in 40 minutes, more or less, so that we can have a discussion later and answer questions between all of us. So yeah, if anybody wants to volunteer, is welcome to do it. And we would love to, explain things, trigger interesting discussions. So the format as we have thought it is like, I'm going to speak now for 40 minutes more or less, and we'd love to have interruptions constantly, as many as you can, like ask questions. In any case, at the end, we will have 10 or 15 minutes for general discussion, in which more questions could be asked, and everybody could answer, right? And then a little bit of the story why we are here. The reason is that about a year ago, I think, a few people in ICMAT, David, Juan, Cesar, Simon, and others started reading a little bit about causal inference, and we decided to create a reading group that started, as I told you, about a year ago. And we started by reading a very famous book by Judea Pearl on causal inference. We finished the book and still we were not super convinced, so we decided to continue, and now we are starting with another book. And we decided that it could be more interesting to have more people joining the sessions, and we made a public announcement, and we have had quite a lot of people interested. And importantly, as we had way more people than we were expecting, there are some people that are out of this, unfortunately, because there was a limit of number of people. So if someone is not going to attend or doesn't want to continue, doesn't have time or whatever, just let us know so we can give the chance to someone else. And I think that's more or less the information is the information I gave you in the email. Yeah, more or less the information I have. Yeah.
So on the email, I don't remember, did you tell the precise book, etc., so that everybody...
Yeah, I sent a link to the book. That's important. And in that link, you can download the PDF that is open for everybody. So everybody can have access to the book. And the other thing is that there is a Google group that we created. So if someone is not in the Google group, just let me know, because sometimes there are problems with the non-Gmail directions. So I added people that maybe is not working for them. So just let me know, and we will use that to share relevant information or papers or whatever. And of course, everybody can send things to that group, as long as they are related somehow with causal inference. Okay, so is there any question, or we should start with?
So should we send you our Gmail address?
Yeah, please send me and tell me, add me to the list, and I will add you as soon as possible.
Do you prefer a Gmail rather than the?
I'm convinced that the Gmail works because it's a Google group. Sometimes other directions work too, but Gmail works for sure. I added you this morning, I think.
Okay.
And so check your. I added you through the FESIC email. So check if that's working. If you received something and you can join, it's working. If you didn't receive nothing, it's not working.
Okay.
So, and then send me the Gmail. Any more questions online?
I'm not the Google Graph.
Okay, so for this person, just pop me an email and tell me preferably your Gmail address.
So you can tell that we are about 40 persons in many places.
Yeah.
So we have a very rich discussion.
Yeah, there is a lot of people from different origins, and yeah, we are excited to start with this. Okay, so yeah, let's move to the first chapter, and yeah, this week is me the one reading it, and I will try to give you a summary. So the first chapter, the goal of the chapter is to define what is causal inference, what is a causal effect, and somehow the chapter finishes with describing the main goal of the book, right? The main goal of the book is to determine under which conditions we can estimate a causal effect using observational data. That's the goal, right? So we are gonna start by defining causal inference, telling you what is the problem of causal inference, and end up at least understanding that we need to define some conditions under which we can estimate causal effects. Defining what is a causal effect is something very complex, extremely complex task, maybe more related with philosophy. But we all agree that everybody has an intuition on what causal effect is. And the reason that we have it is because otherwise we probably wouldn't be alive. We as humans learn this intuition naturally. We know that if I throw this chopstick, this chalk, it will go down and touch the floor. And we learn other things causally, right? If we don't know how to swim, we know that we will probably drown if we are in non-shallow water. So everybody has an intuition, and the goal of the beginning of the chapter is to just make a quantitative definition of a causal effect that we can work with. So we are not going to enter into the details of what a causal effect is, but we are going to translate our intuition about causal effects into some mathematical notation. And here it's important to say that there are two main frameworks to deal with causal effects. There is the framework that Judea Pearl pioneered, which is based on causal diagrams. And there is the potential outcome framework that started with Donald Rubin and some more. This book focuses in the potential outcome framework, and is what we are going to learn. But both frameworks are very similar, I would say, but as it happens usually in science, people confront to each other, right? It's the same fight as Bayesian and frequentists. They confront to each other, and this happens with this framework.
We shall see a little bit on causal graphs.
Yeah. We're going to cover aspects of causal diagrams.
And then the idea is that some of these other papers at the end refer to other frameworks like decision theoretic framework and so on.
Yeah, exactly. Okay.
So is there a key feature between the two different frameworks?
Is there a?
the key features between the two frameworks. Why are there two frameworks?
Well, because they were invented by different people, and each made different decisions. The Donner-Rubin framework is more a statistical-based framework, when the Judea-Peres comes from the world of computer science. They have many similarities. They use tools from each other, right? But still, there are few differences that people don't agree on. So,
Like, give me one example.
like about the difference. The main one is that the framework by the Judea-Peres relies on the use of causal diagrams, and the framework of Donner-Rubin started without relying on those causal diagrams. But then they had to start using them, and yeah, there are a lot of discussions. If you want, I mean, I follow in Twitter Judea-Peres. If you want to follow him, he's very like. I don't know, he discussed strongly against the other framework, and there are, maybe some people know, there are discussions that you can read, which are very in-depth.
Can I make an addition?
Yeah, sure.
The book by Morgan and Winship, Causal Inference, Counterfactuals and Causal Inference in Social Research, actually uses mainly the Pearl's approach, but makes a lot of comparisons with Rubin's approach.
Yeah.
So they actually make it explicit that both of them, most of the time, one can be translated into the other one.
Yeah.
And they establish a lot of the connections. On the other hand, for instance, the book, there's a really nice book by Rosenbaum, which is in the Rubin tradition.
Mm-hmm.
He doesn't use a single causal tag at all in the whole book.
Yeah.
He has a reference to Pearl's book,
Mm-hmm.
but there's no mention whatsoever. I mean, there's not a single diagram of, like, there's not a single tag.
Yeah,
in the whole
yeah.
300 pages full. So it's
Oh yeah, that's interesting. I mean, all those ideas are super useful to us because, first of all, I have to say that I'm not an expert in causal inference. We started reading about it like a year ago. I've read something, but so any idea is welcome. Yeah, those references are useful. Okay, so yeah, the goal, as we say, of this chapter is to introduce some mathematical notation to. I should put this a little bit down. Introduce some mathematical notation to formalize the causal intuition that we all have. And it starts with an example that says that Zeus receives a heart transplant, right? And after 5 days, 5 days later, he dies, right? If somehow we knew that Zeus had not received his heart transplant, 5 days later he would be alive, we all would agree that there is a causal effect of receiving a heart transplant and dying, right? And this means that if there was a parallel world in which everything is the same as in this world, but the only difference is that in that world, Zeus does not receive a heart transplant, then 5 days later he wouldn't have died, then we all would agree that that's precisely the causal effect, right? That's something we have to agree on, otherwise we could not continue. So the reasoning about causal effects is we need to compare mentally. To reason about causal effects, we need to first compare. And this is we have to compare mentally, like it's an exercise, a mental exercise, mentally. Outcome. When A happens, where A is intervention, versus A does not happen. In this example, the intervention is a heart transplant, and we have to compare mentally what would have happened if A happens, if the heart transplants take place, and if not. And if the outcomes is different, if outcomes, which are usually called Y, are different, in these two situations, there is a causal effect. Okay? in this case, the outcome is 5 days mortality, right?
These are you're thinking of the likely outcomes because he could die in the example that you gave. He could die, but he could not die.
Yeah, here in this case is a binary outcome, and it's a binary outcome which has to be precisely defined. It's mortality within 5 days, right? Okay, so that's the goal. So then there is a natural way of Can you see this one? So yeah, there is an the way to define these variables is to give some notation. A is going to be called the intervention, that is also called treatment, depending on the field where you are doing research. Is the exposure, treatment, intervention. All those are same names for the same thing, right? And here is defined as a random variable that can take 2 values. We will start with binary treatments because are easier to deal with. It can be 1 or 0. 1 if treated, if the intervention happens, and 0 if not treated. And then there is an outcome, y, which for simplicity we will start with working with binary outcomes. 1 if, in our example, death, if the patient dies, and 0 if not. And these are going to be random variables in the sense that everybody, like each individual in the population, can have different values for these ones. And now if we want to make a precise definition of a causal effect, we need another couple of variables, which are expressed like this. Y with a superindex A equal 1, and Y superindex A equals 0. These are the so-called potential outcomes. This is what could be the Y value, the outcome value, if the person has received treatment versus the outcome value if the persons have not received treatment. These two are obviously also random variables, right? And in our example, for a particular individual, which was Zeus, yi given treatment was 1, because with the treatment the patient died, and yi equals 0 was 0. Okay? There are different outcomes for the different treatments, and this is what we're going to call a causal effect. Okay? So we will say that A has a causal effect on Y if potential outcomes under different treatments are different for a given individual. So now we are talking about individual causal effects. So causal effect of a treatment in an outcome for a given person, right?
So for another person, it could be...
It could be different. A treatment can have a causal effect for Simon, but not have it for me. This is individual causal effect. And there is an important note here that obviously, as we all are thinking now, we just observe one of these in reality. Right? If we give a heart transplant to a person, we will just observe the outcome, yi for that person with treatment set to 1. Just 1. And there is an axiom of causal inference that is called consistency. Which essentially means that the outcome that we observe for individual I is equal to the potential outcome for individual I conditioned on the given the treatment that this person received. This means that if the potential outcome for Zeus receiving heart transplant is to die, then the outcome for Zeus is going to be death. right? And that's an axiom that that we will be using constantly. This is the way to move from potential outcomes to observations. Okay. But of course, like, as you cannot observe both potential outcomes at the same time, you will just observe one. In general, you cannot estimate individual causal effects. So we are going to stop trying to identify individual causal effects.
Estimating causal effects means assessing the probabilities.
Means, for instance, measuring the difference between the two outcomes, or establishing that the two potential outcomes are different. In this case, we say that as if we measure data for a given individual, we will just observe either one or the other, but not both at the same time. So identify they say that this causal effect cannot be identified. Cannot be identified means that we cannot write the difference of these ones, for instance, using the observed data, because we don't have enough data.
Can I ask a silly question?
Yeah, sure.
You said that's an axiom. Is that the same as an assumption? Statisticians refer to as an assumption, or is there a slight difference between assumption and axiom? I mean, maybe this is a stupid question.
Assumption, I would say, but I'm not sure, but I would say that an assumption, you can prove it false. This is something that you cannot prove false. It's something that is like an axiom in the mathematical sense. Okay. I would say, but I mean, you will never be able to prove this. Okay. To prove this false.
Okay, thank you.
I think so. But
all right.
Excuse me, I have a question. Okay, is there any relationship between this superindex notation, the Y super A, and the do operator of Judah-Pearl? Is it similar to a do operator?
Well, the do operator will come later, and I will make sure that we understand where is the do operator and where is the connection with this framework. But yeah, definitely there is a connection. But also, Judah-Pearl works in this causal ladder that he proposes. He proposes different levels, and the last level is the counterfactual, working on counterfactuals, and this A has to do with that. This indeed, this thing is called under Rubin's framework is called potential outcome, but some other people call it counterfactual. Okay.
Okay, thank you.
I mean, you need this consistency, otherwise.
Yeah. I mean, otherwise.
It's possible to think of something without this. I mean, one of the potential outcomes is the real outcome.
Yeah.
And of course, the real outcome should be equal to the potential outcome.
Exactly.
Otherwise.
It's like, I mean, it makes sense to all of us. It's like, it's an action, right? Okay. So the next thing we can do, once we understand that we cannot identify individual causal effects, the next natural thing is to try to identify average causal effects. Average means across a population. And this is, for instance, what they tried to do when they were testing the coronavirus vaccine, for instance. They were trying to test whether there was a causal effect on being vaccinated and avoiding going to hospital, for instance, or avoiding being contagious, taking the COVID, right? Those effects were average causal effects. Was on average, this is what happens in the population. And we are going to try to define the average causal effect in a population. Average causal effect. And in order to talk about that average causal effects, we would need three ingredients. First, define clearly what is the outcome of interest. For instance, in this example that I just gave you, the outcome would be getting COVID, getting sick of COVID. Actions that we are going to take, and we are going to restrict ourselves for the moment with binary actions, A1 and A0, which could be being vaccinated, taking the vaccine versus not taking the vaccine. And finally, we need to set a population. That we are going to work with. In this population, we will compare Y outcome versus no treatment, outcome with no treatment versus outcome with treatment. And in this example, in this book, they give you a simple example, a population of 20 people, that's the full population of interest, 20 people. We have recorded data in every individual. And they say, imagine for a moment that we have individual 1, 2, 3, and we can measure, imagine, this is not gonna be the case never, but for understanding, we can measure both outcomes. And we have, so this person under no treatment died, and under treatment survived and died, and so on, 1, 0, and they give you some data, okay? So with this data, you can compute the probability of Y outcome under treatment equal to 1, and is 0.5. And the probability of outcome equal to 0, equal to 1, given no treatment, and this is also 0.5 in this example. As these two quantities are equal, we say that there is not an average causal effect. And I'm going to explain why right now. So, obviously, under a binary outcome, it's very easy to prove that the expectation of Y equal 1 is the probability of Y equal 1 equal to 1. This is very easy to understand for binary algorithms. Yeah, sorry. Okay. So we say that an average causal effect of A on Y exists if these two expectations are different. The expected value of the outcome for treatment 1 is different from the expected value of the outcome for treatment 0. Okay? If those two expected values are the same, there is not a causal effect of A on Y. And here they give a couple of technical notes, which I think are interesting, at least to mention. They talk about what is interference. We are making a huge assumption here, which is implicit. And the assumption is that my potential outcome just depends on the treatment that I receive. My potential outcomes depends on the treatment that I received, but not on the treatment that Cesar receives, that other person receives. And this is not always the case. For instance, I went once to a talk in which the treatment was in certain region in Africa was to give an educational program on how to avoid sexual harassment for women, right? So they gave that program in a school, and they noticed that other schools that were nearby were affected by the treatment, in the sense that the people of this school were telling people to the other school, hey, I received this thing, and it's interesting, look, these are the tricks, right, that they taught me. Sometimes, especially in social research, the treatment that you receive can affect the potential outcome of someone else. This doesn't happen when the treatment is eating a pill or with a vaccine in general. But it could happen in social research and in other fields. Okay, so we are implicitly assuming that there is no interference. We are implicitly assuming that my potential outcome just depends on my treatment and not in someone else receiving the treatment. Okay, and the other assumption is that there are no multiple versions of the treatments. Here, the treatment was heart transplant, but of course, you could think of the heart transplant being made by two different surgeons, given possibly different results, or the heart transplant made using different techniques could also give different results. So we are assuming that all the treatments, all versions of the treatment will lead to the same potential outcomes. And those are two assumptions that we are making implicitly that are needed in order to have the potential outcome and the causal effect well defined.
this last one can be extended to, because you're assuming here that they are binary, but if you extend it to.
Yeah.
you could-
Yeah.
yes.
And it's something that is, I mean, in the main assumptions that they make in the Rubin's framework, they include these two.
And you should understand the table. So in this case, the table is telling you that you have just one outcome, and the other one, just because it's a binary result, then automatically is 0. Or is it that you have measured both?
No, you imagine that you can measure both outcomes. Outcome, had the patient received treatment 0 or treatment 1.
Right, but if you were to measure only one, because it's a binary decision, then the other one is then 0 by definition, in case you get one.
No, this could be 1 and 1, 2.
Yeah, it's an imagination.
You can have
Yeah.
a person that would die either way. For example, a person that would die even if the person received a heart transplant, for example.
Sometime later, you will go to observation of that, which you can observe, you cannot observe both, but it's just an imagination.
I mean, and indeed, when these two are equal, it means that for this individual, there is not a causal effect. Because no matter what treatment you give to the individual, the outcome, the potential outcome is the same. So it can be, I mean, it can be 0, 0, 0, 1, 1, 0, and 1, 1.
Okay, so this is a super control experiment, right? Yeah. Observational.
Yeah, no, this is a mental experiment.
Where you can,
It's an imagination experiment.
Yeah.
Not even. not
Yeah,
even-
No, it's definitely not real because you're measuring two counterfactors which are mutually exclusive in reality.
yeah, but let's say that you takes an individual, do the treatment, measure, and then wait for a while, and with the same individual, not doing the treatment.
But those are not potential outcomes.
No.
Because if the treatment is done in different time points, then it's not a potential outcome. Are outcomes of two different things.
But it shouldn't be just basically a theoretical concept.
Yeah, it's purely mental. Yeah, and then just another technical point. What you do in general, if the outcome is not binary, this expected value, just for the mathematicians or statisticians in the room, is simply computed in general as y times. I mean, this is the distribution function, the cumulative distribution function of yi. Okay. Yes, just a technical note. This is in general, and of course, for a binary outcome, this expected value is just this probability. Just a technical note. Well, once we understand what is the definition of an average causal effect, that those two expected values are different, they give us some measures of causal effect, some ways of quantifying average causal effect, and they give us essentially 3. They say that there is no causal effect, or what they call there is the causal null hypothesis. When one of these three things happen, the probability of y a equal 1 minus probability of y a equals 0 equal to 1 is 0. So if these two are the same, there is no causal effect, and this is the causal risk difference. There is the causal risk ratio, in which the quantity of interest is this ratio. And here, in order not to have a causal effect, this has to be 1. And there is finally the causal odds ratio. This is the causal risk ratio. And the causal odds ratio is just probability of y1 equal 1 divided by probability of y equal 1 equals 0, and the same quantity with a equals 0, which are the odds. If this is 1, there is no causal effects. Causal odds ratio. Okay. And of course, these quantities here in the left side of the equalities are measures of causal effect. when do we use some of the others? For instance, in many applications in which this difference could be negligible, like very small, we could use the risk ratio or the odds ratio. And then there is an important part of the chapter, which is, they call it random variability, and explain the sources of variability that intervene when estimating any of these quantities, when estimating causal effects. And there are essentially two sources of variability. One, sampling variability. Sampling variability. So what is this? If we have a population, imagine that we have a population, and let's think of the case in which we can measure all the potential outcomes for every individual, right? Like we have given an individual this population, we can measure both of the potential outcomes, something that we will never be able to, but imagine that. Even in that case, we cannot in general measure every individual in the population. We need to take a random sample of that population, and we need to create estimates of these probabilities, right? We need to create an estimate given the finite sample. This is the classical statistical inference problem. Ideally, we would want to have estimates that are consistent, for instance, in the sense that when the sample size grows to infinity, this will converge in some sense to the real probability. But even in this case, we will never be able to identify exactly the causal effect. We can just measure evidence supporting the hypothesis that there is a causal effect and evidence supporting the hypothesis that there is not. The other source of variability is the random error. The possibility of having non-deterministic outcomes. So now we have talked about potential outcomes, and for us, the potential outcomes were completely deterministic. We were saying that potential outcome Theus had received in the heart transplant is that he would have died with probability 1. That's deterministic. But we could think of a case in which the potential outcome is stochastic itself. We could say that if a person received a treatment, that person could die with certain probability and survive with a complementary probability, right? That's another source of variability. And there is ways to working with this other source of variability. But for the moment, until later in the book, they will assume two things. First, that the outcomes are deterministic, in the sense that your potential outcome, if you take the treatment, is 1 or 0, but is completely determined. It's not stochastic. And the other thing that we will assume that we measure every individual in the population. Okay, so we don't have to worry about sampling variability. And this is like a didactical approach because this introduces complexity. And for the beginner, it's better to work on a much simpler problems in which these two sources of uncertainty are not present. Okay. And just the final thing of the chapter. Which will take us to the goal of the book. They discuss a little bit, once we know a definition of causal effects, they discuss a little bit about causation versus association. They again take the example, but now take the real data. We have individuals, 1, 2, 3. We have the treatment that the individual actually took. 1, they put 0, 0, whatever, 1. And they have the outcome that we measure on the particular individual. 0, 1, 0, okay. So this is the individual, the treatment that the individual took, whether it didn't take the heart transplant or it took it, and the outcome that we see. This is the real data that we are going to be dealing with, okay, not the previous one. With this data, all we can measure is the probability, for instance, of y=1 of dying given no heart transplant. And if you measure in this sample, is 3 divided by 7, and the probability of y=1 given transplant, this is 7 divided by 13. And now we say that when P of y=1 given a=1 is the same as y=1 given a=0, when this happens, we say, and we all know this, that A is independent, this is the symbol for independence, of y, which means that A does not predict y, or A is not associated with y. We see here that in our case, even though there was not a causal effect, an average causal effect of A on y, we observe that A is associated with y. And this is something that we can easily think of. Like, there is a possibility in which, for instance, in heart transplant, like heart transplant is not associated with death. That's a possibility. But we can see, if we take measures, we can see that the people receiving a heart transplant are more likely to die, and they die more. So there is an association between receiving heart transplant and dying. And that's something that could happen because usually people receiving a heart transplant are not a random sample of the population, but are people having certain conditions, certain cardiovascular disease or whatever, right? So we could have an association, but not a causal effect. And this is important to understand. The same measures that we put before for causal effect happen also can also be defined for associational effects. I'm not going to write them all, but they are just the same. For instance, the associational risk difference is the probability of outcome 1 given treatment 1 minus the probability of outcome 1 given treatment 0. Okay, if this is equal to 0, we say that there is no associational effect. If it is different from 0, there is an associational effect. And the other two measures, the associational risk ratio and the associational force ratio, are defined in the same way. And just to finish, there is a picture which is kind of informative. If we have the whole population here, and we have this part taking treatment, and this part not taking treatment, well, it says in the other way, untreated, treated, then causation is determined by comparing the whole population, had the whole population not received treatment versus the whole population, had the whole population received treatment. While association, measuring association, requires comparing the population that actually received treatment versus the population that did not receive treatment. So in this case, we are comparing the same population under two different conditions, while in association, we are comparing two different populations.
So causation is an imagination exercise.
It's an imagination exercise. But now the end of the chapter says, okay, so in general, we cannot measure potential outcomes at the same time, right? The goal of the book is to explain under which conditions we can determine an average causal effect using data. And if you imagine in a statistical way, if you have y=1 and y=0, right? And here you have the treatment. If the treatment received, if the first person received treatment, you observe this value, and this is missing. If the second one does not receive, you observe this value, and this is missing. If this one is 1, you observe this, and this is missing. This is missing. From a statistical point of view, this is a problem of imputing missing values. Under which conditions this imputation makes sense, and this is very related with missing at random. You have to assume certain things. The rest of the book is going to try to work on those assumptions, on those conditions under which we can estimate causal effects. And I think this is all I have. Now we have some time for a discussion, questions or whatever, and if not, we will close the first session.
You can do association, and then use association. If I were to examine this example, something like the association, and then I find that these probabilities or the expected values are different, then I would argue that there's a cause. They causes.
But you need certain, at least to make certain assumption, or at least have a proper experiment design in order to say that.
Before getting to these books, it would be the typical thing that I would do in the data, right? I do this sort of association, and then I find that the probabilities or the expected values are different, then I argue that there's a causation.
Yeah, but
in the real world, I mean.
Yeah, in the real world, I have worked with some doctors, and like the main cause, sometimes you have an association without a causation because there is a confounding variable, right? Which is a variable that affects both the outcome and receiving treatment or not. So the doctors, in my experience, typically measure a lot of variables, and they say, well, okay, let's control for all possible confounding factors. And sometimes like they just try to control for as many things as they can. But in the following chapters, we will try to understand that this is not always the ideal case, right? But of course, in order to determine which variables we want to control for, we need to make some assumptions, some causal assumptions about the nature, right? About the problem at hand. But yeah, what is commonly done is, okay, just in case, let's control for many, many things, measure this difference, but controlled by some other variables here. And if they are different, we'll say that there's a causal effect.
Well, I mean, this is the standard toolkit that's out there, I would say.
Mm-hmm.
So you compute probabilities, maybe you control for some factor, conditional probabilities. And then when you find some difference, then you argue that this is causality.
Mm-hmm.
So, I mean, I would say that this is we have done before getting serious about causality probably.
But I guess they still do pretty much the same.
Yeah.
Except they argue when you can do it, when you cannot, and when you should control for C or W or B, depending on where you think C or W or B are actually related to it. I mean, Hernan has a really nice short course, which is called Draw Your Assumptions Before Your Conclusions. I mean, the whole point there is you should control for things or not, depending on what you think those things are actually doing. So you start by basically you start by drawing the directed acyclic graph, and then depending on where particular variable is located relative to your causes and effect, then you decide to control for them or not control for them or control in particular way. So I guess what you're saying is a standard toolkit, but they sort of like kind of augment it by saying, don't do that, do that. Is this sort of like
Okay, but then the answer is then that you do need this sort of causal graphs.
yeah, you need them.
But
in
even if you
Rubin's
don't
framework,
plot them, basically what you're saying that you have to control for variables, at the end you have a sort of underlying model,
you start with the underlying model actually.
which is supposed to be what Bert is saying.
Hmm.
So even when in this scenario you are not arguing about that, but you might be arguing about controlling this or that, at the end the answer that you are giving.
And there's one of the
model underlying the whole
Yeah,
thing.
yeah.
Otherwise,
And definitely the people using the potential outcome frameworks, when they need to define what are the confounding factors, they rely on the backdoor criteria of like they need to rely on that. Yeah.
Yeah.
But then also, there is value in formalizing these things because then you discover new ways of determining causal effects. For instance, instrumental variable analysis and things like that. If you are sure of what are your assumptions and what you are doing, you can devise new strategies to determine causal effects. Of course, always you need to rely on assumptions, definitely, on causal assumptions. Make sure. Any other thing, question online or something?
So you said, so you estimate the causal effect, and you said this is a completely sort of a thought experiment, right? We need to think about the potential outcomes we have not observed in order to estimate that causal effect. But then can you sort of like move the problem forward and say, okay, I'm doing that when estimating, but then the proof is in the pudding, in the sense that if I then intervene and I get the outcome I want, then I've done the inference correctly. Is this sort of making sense? Like, so you do an experiment to see whether COVID vaccine works or not, and then you estimate the causal effect. But then the eventual sort of, did we get it right? Are people dying? So is this sort of, can you short circuit the logic or not really?
I don't think so. Like, so first, like when you're estimating the causal effect, for instance, for a vaccine, you need to either make a lot of assumptions, or make a control experiment, right? A randomized clinical trial.
But in the randomized trial, you're still making assumptions. Like people are as randomly assigned to one. So those that didn't get the vaccine are equal, are basically the same.
With the vaccine, it's tricky because actually I'm not sure how they make it, because like, I guess, I mean, people not receiving the vaccine, are they vaccinated with something?
They are given a placebo, aren't they?
They are given a placebo, right? Because I mean,
otherwise
in the vaccine case, otherwise you know, and that's important.
Yeah.
In the vaccine, I never thought how they do it, but when you're taking a pill, they will give you a placebo for sure, and in the vaccine, they will give you something else. So yeah, I mean, you minimize the amount of assumptions, but the fact that you're given this treatment at random guarantees in the statistical sense that these missing values are going to be at random. They are not going to be affected by some other variables, and then you can estimate the causal effect. But then it could happen, it could be perfectly the case that you start giving the vaccine, or I don't know, for some, like it's very easy to think in aspirin, right? You can prove with a randomized clinical trial that the aspirin reduces the mortality within a certain time window. And it's an example that is in the book, right? And there's a causal effect. But then it could be perfectly the case that you start giving aspirin to people and you see that the people taking aspirin are dying more. That could be perfectly the case, because people taking aspirin, for instance, are more likely to have suffered from a stroke, right? And that could be perfectly the case. And even in that case, you need to still give the people aspirin because you have proven that there is a causal effect an average causal effect in the population. Even if then what you measure, the association that you measure is inverted, which could perfectly be the case, there is an average causal effect. So the good practice by doctors should be to give you the aspirin. Okay, so yeah, I guess it's been almost an hour now. So if there is nothing else, we close. And remember that the next session is going to be about chapter 2 and it's in December 16th. Same time, Orange Room here, online at the same link. Thank you all for coming.
Thank you. Could you please write down your email so that we can send you an email?
Sure. Sure.
Thank you.
So give me some time, Simon, before disconnecting.
Yeah.
You can.
We're not recording anymore, but
Yeah, but as long as people see. It's this one here. Yeah, and in case I don't reply, but I usually reply to the ICMAT one, this one. Is the same thing, roy.naveiro@gmail.com or icmat.es.
Thank you very much, and thank you for the initiative. It's wonderful to have these sessions. Thank you. Bye.